Good afternoon. Hi. So I want to make sure all of you are submitting your participation exercises. The ritual is if you had a lecture on Thursday, the exercise is due by 2:30 p.m. on Tuesday, that is today. And whatever we do assign today is due by 2:30 p.m. on Thursday. Is everybody doing this? Because if you don't, you are slipping in that grading scale. So please do this. Okay. Today, my plan is to do some examples on equation solving, module 2, and also go over the mock exam 1, answer any questions you may have about the exam. And also today's participation exercises, problem 1 from the mock exam to be done and submitted by Thursday. That is when you come for the exam by 2:30 p.m. You should have done this by 2:30 p.m. on Thursday. So if you have not already started looking at the mock exam, this is a good excuse to do that. It is a difficult or challenging problem that you can expect on the test, and doing this will hopefully prepare you for that. Okay. Before we begin with examples on module 2, any questions about the exam? So somebody asked, I said handwritten notes on the mock. I didn't say how many. No more than 3 sheets. You can write front and back. No printed material. If it's your own notes written on a pad or a tablet, you can print that out and bring it, but no textbook, no printed material. That's what I mean by printed, not your own handwriting.
What about the tables?
I will provide tables. All tables will be provided. T statistic, normal tables, anything that you need, which I think you need, will be provided. You can bring 3 sheets. Yes.
The only tables are the T table and the normal history.
I'll provide that. Yeah. Okay. 3 sheets. You can bring a calculator. No devices, like no cell phone, no tabs, no computers, anything. And we'll have 75 minutes, 5 problems. All problems have equal weightage, so 20% each. And I'll go over the mark later in the class. Okay. Okay. So that said, I want to pick 2 problems from the mock itself that are on module 2. It is problem 2, which says solve using Newton-Raphson. Using Newton-Raphson. It talks about an equation which is e power or exponent of minus 0.1x minus sine 2x plus cosine of 4x equal to 0. Solve using Newton-Raphson method with an initial guess xi or x1 if you want to call that equal to 1. So the problem gives you an initial guess. Sometimes you may be asked to pick one. Perform iterations until the approximate relative error between the root in successive iterations falls below 5%. That is, the stopping criterion is xi plus 1 minus xi divided by xi. Absolute value falls below 5%. Some of you may say, I'll do xi plus 1 minus xi divided by xi plus 1 less than 5%. That's also okay. There is no universal accepted definition for what is relative error, as long as you do something reasonable. Okay. So it will say in words relative error between successive iterations. So you have to tell me what formula you actually use to compute that relative error and then go forward. Okay. So there's a lot of room for judgment and flexibility. I'm not boxing you in. I want you to be exercising that judgment and state the assumption. So how should we begin? So we'll call this function f of x. And if f of x is, I'll rewrite it here, is exponent of minus 0.1x minus sine of 2x plus cosine of 4x. You want to compute the derivative, that is minus 0.1 times exponent of minus 0.1x minus 2 cosine of 2x minus 4 sine of 4x. Thank you. So it says perform iterations until the error falls below 5%. What I would suggest is in a clean sheet, you have a table, you do your work separately and fill out the table and keep it neat there so that you can follow it easily. Don't start a table and then do the calculations. Keep a separate page for table. Okay, that's my suggestion. So I'll say iteration number, that is I, the value of xi, the value of the function at xi, the value of the derivative at xi, and then xi plus 1, which of course would repeat here. So I'll start with iteration 1 and a guess value of 1, and I want to start punching out numbers. Now for those, I see many laptops out, that is great. How about we take 5 minutes to implement this on the computer, keep the answer ready, and then start doing the handiwork so that you can check your own work very easily. Okay, why don't we build a code on Excel? So I'm going to build mine and you can do the same and we'll meet after 5 minutes. Are we good to share our screens? Is everybody able to do the Excel programming? Like set it up in like 2 or 3 iterations, it should converge within 5%, or even actually in 2 iterations. Okay, may I bring down the screen? Okay. So I'm not going to go over this entirely, but I'll just show my sheet and we'll compare each other's and you can see if you got similar numbers. So I have my X iteration number. When you do this on paper, I suggest that you keep the same heading: iteration number, X value, f of x, f dash of x, the next value of x, and relative error, so that you have one full set in each row. And you start with a guess value of 1, which was provided to you. And as you can see, if you had used a different guess value, let's say no guess was provided and you used 0, okay, okay, 0 would cause a problem because it would have division by error. So let's say we start with minus 0.1 as a guess. In that case, it doesn't change much. It just starts a little bit far away. Oh, actually, it converges to a different route. Interesting. Okay, so let's just start with 1. Okay. With a guess value of 1, the f of x, f dash of x, and the next value. And how I compute this relative error is I take the ratio of this with respect to my guess and subtract 1 and express that as a percentage. And then I compute that for each row. So as you can see here, within just 2 iterations, the value falls below 5%. So you can stop after 2 iterations if you did this right. So knowing when to stop will save you time. That's why understanding the stopping criterion is quite important. Okay. So you have this. Any questions? Anybody not able to get these numbers? Yes.
So on the example, we'll need to do all this radians, not degrees, right?
Radians. Whenever you get any trigonometric function on the exam, it is in radians, no degrees. Okay. Yes. Okay. Yeah, sure. So for the function, I have, you see at the top here, I have exponent of minus 0.1 times x, which is in cell C38, minus sine 2x plus cos 4x. Okay. And then I had, again, for the derivative, I had what I had written out: minus 0.1 times exponent of minus 0.1 x minus 2 cos 2x minus 4 sine 4x. So here's what we want. The root is 1.1435. Let's keep that number in mind and do the hand calculation now. A hand calculation is not for my benefit, it's really for yours because you have to do the work on the exam. So let's time ourselves and see how fast you can do this so that you'll know how much time you should spend on this during the test. Okay, so I'm going to time you. Maybe we'll hide this and I'll keep track of the time. Here's my stopwatch. Okay, I'm starting now. Do the calculation. Fill out this table. Do 2 iterations and see how long it takes you. Let's do this. So use only your calculator, don't look at your Excel, and see if you can get to the right answer in how many minutes. I would check back after 5 minutes, okay? So keep working. We'll meet in 5 minutes. Remember, on the exam, you're not going to discuss with your friend, so please do this by yourself. Well, you should check your relative error and see if it converges within 2 iterations. Okay. It's been 6.5 minutes, nearly 7. So I'm going to ask you to take a pause. Let's fill out this table and move on to the next method because we want to do many examples today. So for the starting guess of 1, what is your f of x value that you got? Your hand calculation. 0.6581. Keep 4 decimal points. That's my suggestion. Okay. And then the derivative value is 7690. So the updated value would be, I want to illustrate here, that would be xi minus f of xi divided by f dash of xi. This is the formula. This should be on your sheet so that you can use it. So this would be 1 minus negative 0.6581 divided by 3.7690, which gets us 1.1746, right? 1.1746. Okay. Yeah. Yes.
How many decimal points?
4. That is usually I say keep one more than what is asked in the final answer. If nothing is asked in the final answer, you assume 4 and just go. And okay, so you got 1.1746. So for the second iteration, your x value is 1.1746. And before you move, you should check the relative error, which is 1 minus xi plus 1 divided by xi expressed as a percentage. So that would be 1 minus 1.1746 divided by 1 as a percentage, or this is nothing but nearly 17.46%. So this 17.46 is obviously greater than 5%. So you should continue. This is important. If you kind of miscalculate this, you might be end up doing more iterations than needed and wasting time. Okay, so make sure you do this calculation. Okay, for 1.1746, what is our f of xi? One six three two. Thank you. 0.1632, and f dash of xi would be 5.3150. Thank you again. And xi plus 1 would be, or x3 would be 1.1746 minus 0.1632 divided by 5.3150. So if you do that, you should get something like 1.1439. 1.1439. We again check the relative error, which is 1 minus 1.1439 divided by what? What should I divide here? Sorry, which one?
1 mile above. That's
That is 1. That's a 1. 1.1746. So if you compute this, your relative error would be something like 2.61%. This is less than 5. So you stop. I need to see this. I need to check that you are stopping according to some rational criterion and not because of any other reason. Okay. So you make sure you compute the relative error, compare it with the given tolerance, and then you stop based on some condition being met. All right. So I'll make sure this falls in the camera. All right. Better. Any questions? Yes. It depends how you round it off. If it's you have to take a judgment call. Unless I see the context, I can't give you a universal statement. Okay. So now let's solve the same problem using bisection method, which is a more which is a less efficient method. It will take you more iterations, but we still want to do at least the first 2 or 3 iterations to get the hang of it. Okay. So same problem. Let's try bisection method. Okay. So take a minute, implement that in Excel, and then we'll come back and do this on hand. Yes. So you have to always, so listen up please, there's a question, why did I divide by 1.1746? Your relative error is always trying to see what is the improvement between iterations. So I started this iteration with a value of 1.17 and I updated that to 1.14. I'm trying to see what's the improvement between these two, not the improvement between this and the original case. That's why I'm dividing by 1.17. It's absolute value of that. So whether you subtract this from that or that from this, they are both the same.
I mean, the fraction itself, like, this is 1 minus 1.14, you know,
Yeah,
should the 1 do 1.1746, then xi, or is that always gonna be 1?
so it could be defined either way. So it could be xi plus 1 divided by xi minus 1 or 1 minus that. Since you're taking only the magnitude, it's okay either. Think about it.
Because, okay, that means there's the first one, two of the numbers are gonna be the same,
Yes.
and same thing for the second one.
So this is like writing xi plus 1 divided by xi minus 1 absolute value. This will be like 1 minus xi over xi plus 1 absolute value. They are all nominally the same. Okay, we are doing bisection method now. Same problem. Do this in Excel first, then we'll do the hand calculation. Okay, 5 minutes for Excel. Do the calculation in Excel in about 7 or 8 iterations. You should converge. And then we'll talk a little bit about Excel, how it's my least favorite method. Has a very low probability of being on the test. I want to get to probability soon. I'm rushing. Yes.
This is for the previous one.
Okay.
Here's the thing wrong with this thing. Did you have the negative sign in front for the? You need to put it in the.
Yeah. Negative 0.1 times. You should put a multiplication symbol. Minus 0.1 times exponent, like the star. So the multiplication symbol. 0.1 multiplied. Yep. Now you should also do the same in the second and third. Between 2 and cosine. And between 4 and sine. If you recall bisection method, you need 2 guesses that contain the root. And in our case, that is going to be between 1 and 2. So I'm telling you that, like, use the lower limit of 1 and upper limit of 2. You need to compute the value of the function at the lower and upper, and then compute the midpoint, and then compute the value of the function at the midpoint, and then compute the product of the function at lower times midpoint, and then use that number to judge which should be brought closer, whether A should come closer or B should come closer. So what I suggest is do this row, that is do the first iteration, get up to here, F lower times F midpoint. And then I'll show you how I updated my next row so you can see that and implement. Yes.
Do we use your guess or do we find it?
Right now, if you use my guess, it will go faster, but you are welcome to use your own. It will just take a few more items. Okay, are we good up to here? You don't have to go the full distance right now. Do you have up to here? Then you can look at my formula. Yes? Everybody has multiplied lower and midpoint and has a negative number like negative 1.1. So now the whole point of automation is you should have a criterion for the next iteration that automatically selects based on input from the previous time. So that's what we are going to do here. So look up, please. Take a pause from your laptop. Look up. So I have here. Look up. Take a pause. So I have lower and I have upper. I need to come up with a criterion that you are able to say in words. I need to put it as a statement, right? So what I'm doing here is I'm first checking if this if this product were negative, what does that mean? If lower multiplied by the midpoint is negative, what does that mean? It means A stays the same, the midpoint becomes the new B. Do you agree with me? A stays the same, midpoint becomes the new B. So then Excel says the value if true, if this is true, the A stays the same. So I just have to go for the previous value of lower. And then if it is false, then B becomes the new A. Correct? We're trying to enter what would be the next A. If this product is negative, then the older A is still the new A. If the product is positive, then the old B is the new A. Okay, so I'm putting that here. Then close the bracket. Then what about upper? If this product is negative, what is the new B? Midpoint is the new B. Correct? Midpoint is the new B. If the product is positive, then B is the old B is the new B. So that's my program right there. I'll delete all this and show you that this program would still work. Oh, wait. What happened? Okay, what happened? Not sure. Okay. All right. So I have my new values 1 and 1.5. And then I'll do my second iteration. So how do you check error? So let's say after the first iteration, you get 1.5. That is, of course, not the stopping point because for that iteration, you have produced one updated value, which is 1.5. For the second iteration, the updated value is average of 1 and 1.5, which is 1.25. You need to check these two. That is, I'll say this here. You need to check between these two values, what is the relative error. So the relative error is computed between 1.25 and 1.5. So how I do that here is I say absolute value of 1 minus current minus previous, and then I'll express that as a percentage. So that's 16.67%. Can you make sure that you look at row 31 and 32 and you are able to implement and understand and implement? Then we'll fill out the rest of the rows. There we go. Something isn't right. If this is negative, then B31. If it is positive, E31. That's correct. If it is negative, midpoint becomes the new B. Otherwise B is the new B. Yeah, right. Yeah, okay. Were you able to get the first two iterations? Right? Okay. So if you look at bisection, it gets to the answer. Look up, please. It gets to the answer in about 7 or 8 iterations. Okay. So if you compute the relative error, the error converges at least at the 5th iteration. If you have the 5% criterion, and if you want more accuracy, it takes up to 7 or 8 iterations. And bisection itself is a very calculation intensive method. If you think about it, how many operations do you have to do for single iteration? You have to evaluate the function twice. You have to do one averaging operation and one multiplication operation. And then, of course, computing relative error. That's common for every method. So if you count, it's at least 1, 2, 3, 4 calculations per iteration. In Newton-Raphson, how many iterations or how many calculations do you have to do in every iteration? 2, function and its derivative. In secant method, how many calculations do you have to do in every iteration? You have to evaluate the function at 2 points. That's 2 operations, right? So among all the methods, bisection is the most or the least efficient method, because to advance every iteration, you have to do many operations, much more than the others, like at least 2 more than the others. Okay. So when it comes to numerical implementation, bisection is almost never used, simply because it's not the most efficient algorithm you can find. Okay. One second. It takes a certain number of operations to get the answer, and the number of iterations you need is also higher. Yes.
This, the way that I've been doing this is I'm plugging in values progressing this point. By crossing the midpoint, I'm going to too far, so I can do.
That is also an acceptable way of doing it.
Section. That's only. Even if you that's 2 calculations, even if you just one calculation.
And the last part of your sentence didn't come through. Can you
It's
be
only
louder?
2 calculations. If you're also doing the relative error with each iteration. You know, a couple of them, you look at those acceptably small and you calculate the relative error. It's free.
Okay.
You don't need 4.
We don't need 4. This is the most basic version that we can do. There are variants that are better. And for each method, there are several variants which are made more efficient by making changes. But for this most basic version, it takes 4 operations. That's what I said.
Is this the way you want us to set this up for the exam?
That's what I'm coming next. So having said that this is not the most efficient method and it's not the one that you would actually implement in a project, I'm not going to ask you this on the exam. No bisection method on the exam. I want you to know why I don't. That's why I went into this. There will be 2 problems, one on Newton-Raphson, one on secant method. It probably will be the same problem asking you to solve it twice using 2 methods. Okay, so on the exam, it will be only Newton-Raphson and secant method. Okay. All right, good. So that gives me about 40 minutes. So what I would like to do is ask you to do the secant method by yourself. This Excel sheet has the solution done with secant method, which you can cross check against yours and also do the paper calculation and practice. Okay. So I'm going to stop module 2 here and jump back to module 1 and talk about some of the mock exam problems. All right. But please go through with this because secant will be on the test. I'm telling you right now, secant and Newton-Raphson will be on the test. Okay. All right, good. So we'll do problem 1 first. It seems very complicated. Did you guys take a chance to take a minute to read it? Have you read it? Okay. So if you haven't, please take a minute, read it. We'll talk about it. Okay. A colloidal solution has a particle density of 10 power 9 particles per cubic centimeter. That is, every cubic centimeter of solution has 10 power 9 particles. 10 power 9 is like what? A billion. Every cubic centimeter of that solution has a billion particles. Okay. A sprayer generates droplets whose diameter is normally distributed with a mean value of 15 microns and a standard deviation that is 10% of the mean. So what is standard deviation? 0.1 times 15 microns or 1.5 microns. Okay. If M is the number of droplets, if M is the number of particles per droplet, estimate the fraction of droplets containing no particles, that is M equal to 0, no less than 3 particles, that is M greater than or equal to 3, and no more than 1 particle or M less than or equal to 1. So before you do any calculation, and of course, lastly, assume that the number of particles in a droplet are distributed according to the Poisson distribution. So imagine this, there's a sprayer, makes a lot of droplets, okay, like your garden sprayer or lawn sprinkler. Each droplet has some number of particles. So each droplet is a piece of that solution. And I told you that solution has a billion particles in every centimeter cube. That doesn't mean that every droplet will have particles. Some droplets will be empty, some will have 1, some will have 2, some will have 3. And that number M is distributed according to the Poisson distribution. So what do you know about Poisson distribution? Poisson distribution, what is unitless? Sorry. The lambda is unitless. Okay, good. So what is lambda here? What is the lambda parameter for this quantity, which is number of particles per droplet? Sorry, come again. Particle density. Okay, particle density, which is number per cubic centimeter. Okay, you're saying that is lambda. I'll come back to you. What did you want to say? Lambda is the mean parameter. So what mean of what? Average number of what? Yes. I was doing this all these 5 minutes.
No, I don't get the.
What do you didn't get? You want me to just go over the whole thing again and take me 10 more minutes?
No, like situation of what's going on. I don't understand the density and the particles in the droplet.
What about it, don't you understand? Okay, so what I will briefly say is we have a solution, like imagine a beaker containing some 20 ml of this colloidal solution. If you take a centimeter cube of that liquid, it will have a billion particles. That's what it meant by particle density of 10 power 9 per centimeter cube. It's like mass density except for number. Okay, so there is a billion particles in every centimeter cube, and then we have a sprayer that makes droplets. Each droplet has a diameter, and that diameter follows normal distribution. And that mean value is 15 microns. Standard deviation is 10% or 1.5 microns. So imagine a small droplet. I'm going to stop the sharing here so that I can draw this and explain. So you have a beaker. Let's say there is some large volume. Every centimeter cube of this contains 10 power 9 number per centimeter cube. Okay. And then we put it through a sprayer which makes droplets whose size can vary. That's why it is a distribution. Not all droplets are uniform. And the droplet diameter, let's say, is D. And this D follows normal distribution with a mean of 15 microns and a standard deviation of 1.5 microns. Are you with me so far? Okay. So the question is, these droplets will all contain particles, and each droplet will have, let's say, M particles, and this M follows Poisson distribution with a mean parameter of lambda. My first question to you is, how do you calculate this mean parameter lambda? Every droplet or every centimeter cube contains 10 power 9 particles. Every droplet will have a volume of pi by 6 d cube. Do you agree with me? So how many particles are contained in each droplet?
Yeah.
Louder, please, for everyone.
Multiply the density by the
Multiply the density by
diameter.
diameter. Okay, I'll give you a clue. Diameter cube. Or in other words, you are trying to say multiply the density with the volume of a single droplet. Right? So if I ask you what is the total mass of air in this room, what would you do? You would take the density of the air in this room multiplied by the volume of this room. That will give you mass of air in this room, correct? Right? Volume multiplied by density. Same thing, density multiplied by volume will give us number density times volume of a single droplet equals what? If I take the density multiplied by the volume of a single droplet, what am I getting here? It's the number of particles in a single droplet. Right? It will be the number of particles in a single droplet. Now, what's the unit for number density? Number per centimeter cube. Right? That's what we were told. And what's the unit for droplet volume? Centimeter cube. So this should be a number. That's good. Okay, that's good. And this is equal to nothing but the lambda parameter for a droplet whose diameter is d. As example, if d is equal to 15 microns, which is 15 times 10 power minus 6 meters, or 15 times 10 power minus 4 centimeters, lambda parameter would be pi by 6 d cube multiplied by n naught. So this is pi by 6 times 15 times 10 to the minus 4 cube multiplied by 10 power 9. You can simplify this. We can do that. This number would be 1.767 or 1.76. Let's say 1.77. So lambda, the average number of particles per droplet is 1.76 or 1.77. Take a minute and try to interpret 1.77 for me. How do you think 1.77 particles is even possible? That's no, not that way. That is, if you say 1.77 and then you say this number follows Poisson distribution, we can calculate what is P of 0, P of 1, P of 2. What I'm really asking is 1.77, it's like saying many droplets have 1, many droplets have 2, some have 0, some have 3, fewer have 4, fewer have 5, even fewer have 6. There is a finite chance some droplet will have 8 particles. The average of all of those combines and results in 1.77. Okay, so now if I have 1.77 as my mean parameter, you know how to calculate P of 0, correct? What is P of 0 according to Poisson distribution? Exponent of minus lambda, lambda power 0 divided by 0 factorial. So that's like writing exponent of minus 1.77. So this is like saying the percentage of droplets having no particles. That is exponent of minus 1.77, which if I compute, that's like 17.08 or about 17.1%. Go ahead, do this calculation, get that number on your screen, and you'll feel better. Something not clear? Perfect. 0 factorial. So this is exponent of, so the formula is probability of m being a finite number or probability of getting m events is e power minus lambda, lambda power m divided by m factorial. And m happens to be 0 over here. So take a pause. If this solution were put in a sprayer that just made 15 micron droplets, nothing else, only 15 micron droplets, then 17% of the droplets will contain 0 particles. That's the interpretation. So I'll write it in words here. If the sprayer generated droplets of 15 microns diameter only, then 17.1% would have m equals 0 particles. Yeah. So can you tell me what will be the fraction or probability of particles that contain exactly 1 particle? Come again? 50? Exactly 1 particle. So I want to calculate what is the probability of m equal to 1. That is like asking for e power minus lambda, lambda power 1 divided by 1 factorial, or this is exponent of minus 1.77 multiplied by 1.77. You can tell me that number. Are you getting 30.2? Probability of m equals 2 is exponent of minus 1 point, sorry, m equals 1 is exponent of minus 1.77 times 1.77, which should come out as 30.2%. Are you getting this? Yes? Just looking for some nods around the room, I'm getting a few. 30.2%, are we getting? Yes. Okay, good. So then one of the questions was, what is the probability that what is the fraction of the droplets that contain no more than one particle? So when I say no more than one particle, that's like saying probability of m less than or equal to 1. That includes probability of m equals 0 and m equals 1. So that should be 17.1 plus 30.2 or about 47.3%. What's the interpretation? Nearly half the number of droplets have no more than one particle. They either have 0, they are vacant, or they have exactly one particle. Keep remembering this. All these calculations are assuming we have a fixed diameter of 15 microns. Okay, fixed number. Keep remembering that. We'll revisit that. Okay. With me so far? Yes. Are we okay? Okay. So then another part of the question asked for. It asked for how many, estimate the fraction of droplets containing no particles. We already answered that. That's 17.1%. Contain no more than one particle, that's 47.3%. And then the question goes, what fraction contains no less than 3 particles? How do you define no less than 3 particles? Sorry? First, tell me in words. When you say no less than 3, what is it mathematically?
It would be the probability of 0, 1, and 2.
No, no less than 3. It should be 3 or more.
Greater than or equal to.
Greater than or equal to 3, right? So probability of no less than 3 is like writing probability of m greater than or equal to 3. What I suggest is you write it out, right? This is probability of m equal to 3 plus probability of m equal to 4 plus and so on up to infinity, because theoretically it could have an infinite number of particles. This is 1 minus probability of m equal to 0 plus probability of m equal to 1 plus probability of m equal to 2. Yes. Okay. So you already know probability of m0 and m1. You still need to compute m2. Go ahead, compute m2. So probability of m equal to 2 is exponent of minus lambda squared divided by 2 factorial. This is exponent of minus 1.77 times 1.77 squared divided by 2. Please crunch that. Please crunch that number and tell me. 26.7%. So that's 26.7%. Okay. Yes. No, this is not Z table. This is Poisson distribution. This is not normal distribution. This is all entirely this single formula, Poisson distribution. The Z distribution, Z table is for normal distribution, which is a continuous distribution. This is a discrete distribution. So they are very different. So we still have to get the answer, which is 1 minus probability of M0 is what? 17.1. Thank you. 17.1 plus 30.2 plus 26.7. So you compute this and figure out how many droplets contain no less than 3. 26.1. Thanks. Again, recall, this is assuming if the droplets are all uniform and all have the same size of 15 microns. Okay. Are we good so far? Yes. Are we good so far? Yes.
We have all the bracket, right? I got 73.
Some of these three.
I got 73.
One
73.
minus the sum.
1 minus the sum. Check your calculator. Okay. So this solution here, how many of you think this is what you need to turn in for problem 1? You don't want to raise your hand, at least you know in your mind if you really think this is it or there is something more. What are we missing here? What did the problem ask? What did we compute? M equals 0, M equals M greater than 3 or M less than 1 and so on, right?
They're just asking us for n equals 2.
No. Okay, let me rephrase the question. So we did all this calculation assuming droplet size is 15 microns. Is that what the problem wants? The problem says the number or the droplet diameter could be a number which has a mean of 15 microns and has a standard deviation of 10% and follows a normal distribution. Meaning, if you draw a bell curve, and the mean value is 15 microns, we are saying D can assume values that fall on the bell curve with the standard deviation of 1.5 microns. That is what the problem asks you to do. So what I showed you is how to do this calculation if you had a fixed diameter. How do you generalize this to say, to compute the same probabilities when the droplet diameter can be a random number that assumes normal distribution? That's what the problem asks. So between now and Thursday, you guys have to think, figure out this, how to do 2 distributions. Don't worry about being perfect. I want you to attempt it. While you attempt it, you learn so many things. Upload your sheet or the picture of your sheet showing that you tried and there was reasonable effort. Will give you points. We are not scoring this like by a rubric. If there is reasonable effort, it's not a blank sheet with just a name, we'll give points. Something that's reasonable will provide points. I want you to try, bang your head a few times and then learn and then submit the participation exercise. Okay. So I'll give you some clues. Here is where we compute the lambda parameter for a droplet of diameter D, whose volume is pi by 6 d cube. And then we say here is the number of particles in a single droplet of diameter D. Okay, listen up. Okay, no need to write. This is all getting recorded also. Can I erase this part? So previously, we did D equal to 15 micron as a constant or a single value. Now, D follows a normal distribution with mean of 15 microns and standard deviation of 1.5 microns. So what is the lambda parameter now? Don't give D a specific value, just call it D and keep remembering that D follows a distribution itself. So what is lambda parameter here? N naught VD or N naught pi by 6 DQ. Okay, N naught pi by 6 DQ. What is the probability that M equal to 0? According to Poisson distribution. If, no, not the number, the formula. Not the formula, it's not the number, I want the formula. E power minus lambda, lambda power 0 divided by 0 factorial. Right? Except lambda is not just a number, it's no longer 1.77, it itself is a function of D. Yes, it itself is a function of D. So this is like writing exponent of minus lambda, a function of D. With me? I'm asking, what is the probability of M equal to 0 that takes into account the fact that D itself is a distribution that varies between, or D is a normal distribution with mean of 15 microns and standard deviation of 1.5 microns. That is my question. I want this averaged over the possible values of D. Take a minute, think about that statement, tell me if that makes sense. I'm not interested in just the probability which is a function of lambda. I want it averaged over all possible values of D. We'll come. Does that statement make sense? Yes.
I still don't understand. What do you mean by, are you saying this is like the fraction? Like, what do you mean average?
Okay, it's a good question. So she's asking, what do I mean by averaged over? Okay, so here is lambda. It depends on D. If you had a droplet that is 15 microns, okay, you would have a certain value of lambda. If you had a droplet that is, let's say, 30 microns, you would have a lambda that's 8 times bigger. Do you agree? If I double the diameter, then the lambda value will increase by 8 times. Yes? So what I'm trying to say is lambda scales with dq. And D itself has a bell curve distribution. So some of the larger values of D will contribute more. Some of the smaller values of D will contribute less because the scaling is dq. With me so far? If I want to account for all those contributions, here is lambda. Here is a probability that depends on lambda. I need to write, here is e power minus lambda of D. What is the chance that D will assume a certain value? Go back to the very definition of probability density and tell me what is the probability D falls in a certain range. Yeah. You can't have an exact value at a point. You can define it over a range. I'm asking, what is the chance that D will assume a range of values? No, that's not uncertainty. I'll tell you uncertainty. So some recap here. Okay, if x is a random variable, what is f of x? F of x dx is the probability that x takes values between x and x plus dx. So this f of x dx is the chance that x lies between a certain range. Now, if I say this lambda depends on diameter, what's the chance that the diameter will take on a certain value? That is nothing but the distribution of diameter multiplied by d of d. Or maybe I should start using dp to distinguish. This is the probability or function that I am interested in. This is the chance or probability that d assumes a certain range. And you do know that dp can vary from 0 to infinity. So this is the part I'm saying averaging over all possible values of d. Not only taking into account the function depending on d, but the range over which d itself can vary. So you have to do an integration here. So we'll go back here. You go back here and write probability of m equal to 0 that's averaged over all possible values of d is 0 to infinity e power minus lambda d or lambda of d f of d d dp. Okay, I can see some smiles, some wry smiles. People are like, no way. Okay, so I've given you clue up to here. What I need you to try after this is you need to plug in the normal distribution. Okay, and you need to attempt to do this integral. Attempt this integral. And you still need to pick out an answer in the end, like a number. Previously, you got, what was your number? 17%. Previously, it was 17%. What is it now? When you account for the fact that the diameter is not a single value, but something that could span a wide range with a certain normal distribution. Something like this is coming on the test, I'm telling you now. This is one of the problems. The other 4 will be fairly straightforward, but this will challenge you or something like this.
On the exam, we would be expected to integrate that.
In the exam, you will not be tested per se to do some brute integration. If it comes down to that, maybe it will be like set it up to here, or I'll give you a clue on how to integrate it, or I'll give you an integral which you can directly parachute in. It will not test you on your integration skills. It will test you whether you can reason up to here. This whole problem is this one statement. Previously, you did this for a single droplet diameter. Things were nice and easy. You got your 17.1%. If you can reason up to this point, you basically get all the credit because this is the core here. Yeah. That is to show you how to do this in a simplified way so that you will understand this point. Like you can't directly jump to averaging over the diameter values without knowing how to compute it for a single diameter value. That is not what is asked. It is still helping you learn, but that is not what is the question being asked. Yeah. So this concept is what you need to understand or get your head around. something that uses this concept of averaging over a distribution will be on the test. Okay. I have about 7 minutes. There is another problem on the mock that actually will help you understand this. I'm going to talk about that. Okay. Yes.
Can you talk about number 4?
That's what I'm going to talk. Yeah, number 4. Okay. All right. Let's quickly go through number 4. People have taken pictures, I hope. Okay, I'm going to quickly discuss number 4. Please listen. It's getting recorded, so I'll ask you to just listen. So number 4 reads as, if the probability density of the size of pebbles found in a beach follows a normal distribution for the diameter d measured in centimeters and is given by f of d equal to a exponent of minus d over 3 for d positive. So this is a distribution for the size of the pebbles measured in centimeters given to you. Firstly, the question asked, what is the value of A? Okay, to do that, you need to use the fact that the sum of the probabilities over all possible values of D should equal to what? 1. So that's like saying 0 to infinity, A e power minus D by 3 dd equal to 1. Solve for A. You can do this, right? This is a definite integral with a finite value. You have to calculate it and invert it to get A. The second part is the clue for you. Estimate the average mass of these pebbles, assuming they are perfectly spherical and have a density of 2 grams per centimeter cube. If this D represents the diameter in centimeter, okay, what is the mass of a pebble? Mass of a pebble whose diameter is D. Can you tell me? What is mass? Mass is density times volume. Density multiplied by volume, pi by 6 d cubed. Mass of a pebble with diameter d. We are asking, what is the average mass? What is the average mass? That is like saying, I have the mass, but d is not a single number. D follows a distribution, and that distribution is f of d. So this should be, average mass would be f of d dd integrated from 0 to infinity. So this is like saying mass of d. This is the probability of d taking a certain range. So this average mass would be, we'll call it m bar or m within a triangle with a d subscript. It is the average over the distribution. Average over the distribution. So m bar would be 0 d equal to 0 to infinity rho times pi by 6 d cube times a exponent of minus d by 3 d of d. Okay, so this would be rho is a constant, pi by 6 is a constant, a is a constant. So I'm going to write rho times a multiplied by pi over 6 times 0 to infinity d cube exponent of minus alpha times d of d, where alpha equals 1 by 3. Or this is like writing rho a times pi by 6, 0 to infinity x cube e power minus alpha x dx. So this you would integrate by parts. In worst case, I might provide you this integral. Like I'll say, I'll just give you a number or a formula saying x power n e power 0 to infinity x power n e power minus alpha x dx equal to a formula that depends on n. You should be able to plug it in and get me the final number. Okay, this I would say is a problem a diligent student would be able to do. So like you've been trying all the problems, this should be looking possible. Okay. So on Thursday, I'll be in my office in the morning, like from 10 or maybe 9:45 until the exam starts at 2:40. So until then, from 9:30 to 2:30, except of course the time I teach my other class at 11:20. Okay, I'll be available on Thursday around 9:50 to 2:30, except 11:10 to 12:50. This is on Thursday. Okay. For tomorrow, email me. We can set up a time or do Teams, or in worst case, I might send you my cell phone number to give me a call if you really need urgent help. We'll figure something out. Okay. So tomorrow, email me. Thursday, I'll be in my office if you want to talk. Thanks.